Right now we'll have a short talk by Milos Meriak and Ciro Katutu, who will tell us how RFID can be used to reveal social contacts and give us some statistics on the little experiment that they've been doing during this very Congress. And that's hopefully going to be very interesting. Unfortunately, the third person, Aesthetics, won't be here today because he's ill, but I hope it's nevertheless going to be very, very interesting and you can enjoy the talk.
Hello everyone, I want to welcome you in our Open AMD talk, where we want to tell you what our findings were with the current instance of OpenBeacon and Open AMD. We tell you about what new friends we found which built on top on Open AMD. We'll show you what data we can retrieve with the current versions and what the implications are. We will give you a short introduction to the hardware so you get an idea what the capabilities are and thus what the implications are. And we will show you what the current status of our data mining efforts is and how our web APIs could look like. And yeah, unluckily, we had a lot of misluck with this project, so this is only shows at the end that people now also get ill, despite the fact that they had to work very hard to compensate other people that went missing along the project progressed. So just to say it in advance, this project was only possible because very few people worked really, really hard the last say 2 or 3 weeks and made this possible, especially people like Aesthetics, who unluckily can't attend here. He did amazing work with the data mining APIs, and unluckily we can't show you his part of the presentation, but we try to do our best. And Ciro, which is basically one of the new friends of OpenBeacon AMD, is presenting a group that built very nice software on top, which shows what data is actually there from the data we retrieve. So the first time it's actually visible, not only to mathematicians and sociologists, what data is there, but really everyone can point their browsers to our website, and it's very visible what amount of data results, and therefore you have to ask yourself if you really have nothing to hide. Okay, so let's give a brief introduction to the OpenBeacon hardware. OpenBeacon exists since something like 4 years now. It started basically when we were discussing with a friend how to basically enable scientists, for example, to examine crowded situations where people get killed because panic situations emerge. And the background back then was that people regularly got killed in Saudi Arabia on the Hajj, on the yearly Hajj, because you have this huge crowded situations there. People have to fulfill waypoints there, and you have huge cities of tents. When a fire starts, people get panicking, and basically more people are killed by the resulting panic than by the actual fire. So we thought about, okay, how could it look like if you want to track a huge amount of people? Obviously, there are several existing technologies available, namely low-frequency RFID and high-frequency RFID. You probably know low-frequency well, which is basically the 100 kilohertz approach, which is used in cars still, and basically in huge sports events. 13.56 megahertz you probably know very well from your travel passes or your subway tickets. And all these existing possibilities share the problem that you have to provide a very tight net of readers around a city, for example, if you want to track people. So we try to find a novel approach where the basic design pattern was that it has to last at least a few weeks, and that it's easy to deploy. Obviously, if you have to control a huge crowd of people, you can't lay wires everywhere and stuff like that. So you need a wireless approach, and because current technologies are very low power, namely 2.4 gigahertz, and 2.4 gigahertz is available worldwide, we decided to stick to 2.4 gigahertz because we learned the more generic your system is, the more people can contribute. Therefore, we not only wanted to make this RFID tracking project possible, but we tried to create a very generic hardware platform which enables, for example, scientists to create micro-netting networks or wireless sensors and everything. So every, for example, tag, maybe few people of you bought, is, for example, able to receive and transmit data, which I'll later explain. Because in this particular instance of OpenBeacon, all your tags you currently wear started to talk to each other. Last year's version of OpenBeacon was pretty simplistic. We didn't want to take chances. So the tags were just blindly transmitting, no matter if there is a tracking infrastructure available, no matter if you're on the BCC, they were just transmitting constantly their beacon packets. Although they are encrypted, so you can't be tracked by others, only people that know the secret key we use in our firmware. But it was a very stupid protocol. The background is that it's very cheap in terms of power consumption to transmit short packets. In the case of 2 megabits, the packet transmission is surprisingly low. So the actual packet on air takes 600 microseconds. So even if a crowded situation we have thousands of people, the likelihood of a collision is very, very low. So we thought, okay, that's easily possible to build a tracking upon this technology. And by getting rid of the back channel, which could result in freezes of the system, because if, for example, imagine 1,000 people talking to a reader and saying, hello, I'm here, and they will obviously cancel out their own transmission, and they will obviously have to repeat this transmission if there is the connection fails. Thanks. This could result in lockup. So therefore, we took no chances, said, okay, we make a very simple version. Privacy is a top priority for us, so we wanted to make sure that whoever has access to this data, this results in well-defined conditions. So basically, we are in control what we get and what data we release afterwards. And obviously, it needs to be fail-safe, because you think about a technology, say, okay, it might work, but obviously at some point you have to spend actual money to build 1,000 of these devices and to simply try it out. So if in case of a failure, this could obviously result in a problem. So, but this year we decided to bring, with the help of Tiro, to a new length, and by introducing tags talking to each other. So additionally to the announcement of the former OpenBeacon protocol, which basically on a scheme where you have transmissions on 4 power levels, and the resulting packet loss is used to determine the actual distance to every reader. You additionally have a second channel where you have encrypted transmissions between all the tags, and here every tag can find out about other tags in its proximity. So every tag is now a sniffer and registers incoming packets, decrypts them, takes the tag ID out, and retransmits them along with the normal tracking packets to a server. So we slightly changed our format, and the results were really mind-boggling what data was made available with that. And Ciro will now explain you what they did.
Thank you. No. Boop. Can you hear me? Yeah, I guess so. Okay. So first of all, I would like to thank the organizers and the program committee of the CCC for having me here, and I would like to thank the OpenAMD and Open Beacon team here at 25C3, and in particular Brita and Milos Merjak for their support and very interesting and exciting interactions. What I will talk about in the next 25-30 minutes is a project that we started building exactly on top of the Open Beacon platform at the Institute for Scientific Interchange in Torino. Most of us are actually physicists, and our interest here is not in the physics of the devices, but actually in what kind of patterns and network structure you can mine in terms of social activity when you deploy these devices inside the community in a closed environment. Very briefly, this is the outline of the next 20 minutes. I will show you how we can modify the platform developed by Milos and his team in order to detect reliably face-to-face social interactions. And then I will show you what kind of results you can get by focusing on a couple of small-scale conferences that we performed, that we studied back in Italy. And I will show at the end some very early, very preliminary results regarding the experiment, which is currently running here at 25C3. If you have any questions, feel free to interrupt me at any time. I enjoy that. Okay. So, why do we want to detect contact between people? There are many reasons. The problem is the following. Imagine that you have a room, like it happens in many places in this building, where you have groups of people interacting, talking socially with each other. Basically, what you want to do is, ideally, to mine in real time these kind of structures. Okay? Groups of people interacting socially with each other. Now, by interacting socially, you can mean many things. In the following, I will mean just a face-to-face interaction, which is usually a good proxy for a social contact. It means if you spend 10 minutes in front of each other, within 1 meter, you're probably doing something together and probably talking. And okay, so ideally, you want to mine this graph structure from the real-world data of social contact. And why do you want to do that? This may be a reason, but basically the problem is that we lack fundamental knowledge on human contact. I mean, paradoxically, we know much better how the surface of the moon looks than what are the statistical properties of the contact between people. And these statistical properties, knowing how many contacts are there, how do they last, this kind of information is crucial because to date, a lot of information is somehow riding on these contacts. So you can easily imagine that in the future we'll have peer-to-peer mobile content distribution platforms, and they will rely and they will have to be designed in order to be aware of these contact partners. There are reasons which are even more practical. When you study epidemics, when you study airborne diseases such as SARS, for example, you would like really to model a scenario in which a person in here has an airborne disease, something serious, and you ask the question, okay, at the end of the day, how many hackers are sick? How many will be dead in a week? Okay? So far, basically, there is no fundamental knowledge that would allow us to model this kind of processes. And most epidemiological models model the interaction in closed spaces as a random graph, and as I will show you, this is absolutely not the case. And so there are a lot of heterogeneity, there are a lot of features which actually make the spreading of diseases very different. Okay? So we lack this knowledge, and these are all scientific reasons, I already mentioned this. And then there is another issue that ideally, we would like to integrate in real time data from the real world, from sensors, with data from online systems. So you have seen that on the web during this conference, it was available a web client showing your ego network, the network centered on you, showing your friends, the friends of your friends, which contacts were actually active at the time. If you push this one step further,